Hi, I'm Chao Wei Huang from National Taiwan University. I'm presenting our work, Learning ASR-Robust Contextualized Embeddings for Spoken Language Understanding. You can reach out to us via email, and the source code for this project is available at this link, this GitHub repository. Let me show the highlights of this work. First, we show that when we train a language understanding model on some NLU dataset with contextualized embeddings like ELMO, and if we evaluate the model on spoken dataset with ASR errors, the model doesn't really transfer well. So the domain shift and ASR errors degrade the performance of the contextualized embeddings. And second, we proposed a fine-tuning method to tackle this problem. So you can think of this work as trying to build a bridge between ASR systems and NLU systems. The reason why we're doing this is because if we are trying to do spoken language understanding, an intuitive way is to use a pipelined approach. So first, we have an ASR system to transcribe the spoken utterances, and then we feed the transcription into an NLU system to do the understanding part. This method is pretty simple, but with a caveat, which is ASR systems have arrows, and the arrows will propagate to the downstream NLU tasks, so which will degrade the overall spoken language understanding performance. So in this work, we try to mitigate the effect of ASR errors. Specifically, we are focusing on contextualized models, which is ELMO in our case. So why do we focus on ELMO? It's because pre-trained language models are the current state-of-the-art models for language understanding, but they are mostly pre-trained on written text, such as Wikipedia or some books. So we want to raise a question here. Do they transfer well to spoken domain with ASR errors? For this question, we did an experiment. We trained a language understanding model on manual transcription, which has no ASR errors, and then evaluate it on either manual transcripts or ASR transcripts. Here's the result for this experiment. We tested this on 3 different datasets. We have ATIS, SNPs, and SmartLights. Since the SNPs dataset only has written text, we synthesize speech with a commercial TTS system. We also show the word error rate of ASR results here. The blue columns are the performance when evaluating on manual transcripts, and the green columns are evaluated on ASR transcripts. So as you can see, the performance degrades a lot when ASR errors present. So we can ask another question here. How can we transfer them to spoken domain better? Let's dive into our proposed method. We propose to add an additional fine-tuning stage when using contextualized embeddings like ELMO. Usually when we use ELMO, we have 2 stages. The first stage is language model pre-training, And the second stage is training a target task classifier with the pre-trained language model as feature extractor. We introduce an additional stage in the middle here. The goal of this stage is to make the contextualized embeddings more acoustic aware. And after fine-tuning, we replace the pre-trained model with our fine-tuned model and train target task classifier as usual. Yeah, so how do we make them acoustic aware? We use a very intuitive approach in this work, where we try to force the embeddings of acoustically similar words to be closer. For example, we have 4 embeddings in an embedding space here, which are fares, affairs, flights, and lights. We know that fares and affairs sound similar, and also flights and lights sound similar. So we can use a cosine distance loss here to force them to be closer, just like this. And we call this loss function confusion loss. The problem here is how to determine which words to bring closer. We propose methods for 2 settings. In the first setting, we assume that we have paired ASR and manual transcript. We call this setting supervised since we have paired data. And in the second setting, we assume that we only have some ASR transcripts, and we call this setting unsupervised. For the first case, we can align the manual transcript with ASR transcript, and we know the erroneous word and its correct counterpart. So for example, we have 2 utterances here. One is ground truth transcription, and the other one is ASR transcript. We can align them so we know the word affairs is wrong, and it should be fares. So we should bring the contextualized embeddings of these 2 words closer. So that's how we extract the pairs in this setting. And in the second case, we don't have the ground truth transcript to align. So we extract word confusion network from ASR system, which contains multiple hypotheses, and they are already aligned. By doing this, we know flights here and lights are confusing to the ASR system, so they are probably acoustically similar. So we should bring their contextualized embeddings closer. And so this is how we extract pairs in this setting. And since we know ULM fit proved that fine-tune with language modeling objective helps domain transfer, so we incorporate language modeling loss in the fine-tuning stage. So the final loss for fine-tuning is a linear combination of language modeling loss here and our proposed confusion loss. And here we have the final loss term. And after fine-tuning, we can train a target task classifier with the fine-tuned language model as feature extractor. Here's the results for our experiment on 3 different intent detection datasets. The first column here is the performance of using pre-trained ELMO and evaluating on manual transcripts, which can be seen as the upper bound performance because there is no ASR errors. The second column here is the performance of using pre-trained ELMO but evaluating on ASR transcripts. In the third column here, we fine-tune the pre-trained ELMO with only language modeling loss, which is equivalent to ULM fit. And the last two columns here are the performance of our proposed method in two settings, supervised and unsupervised. As you can see, using only language modeling loss here in the third column to fine-tune improves the result. And after adding the confusion loss that we proposed, the performance improves even more. These results show that our method can learn contextualized embeddings that are more robust to ASR errors. So the conclusions are contextualized models like ELMO do not transfer well to spoken domain with ASR errors. And we introduce an additional stage, fine-tuning stage, to make embeddings more acoustic aware. And we achieve these by forcing embeddings of acoustically similar words to be closer. And we also propose two methods to extract these pairs in different settings. The experiment results show that our method can make contextualized embeddings more robust to ASR errors. Our source code is available at this GitHub repository here, and feel free to contact us if you have any questions. Thanks for listening.